Tim and Neil asked me if I could give some introductory material on just general multi-core memory caching issues. So that's what I'm going to do for this afternoon. I hope that this may be familiar to some of you, but hopefully the exercise will be interesting, even if the background's familiar. What I'm going to be doing is just giving some basic lectures, generic lectures about caching, memory issues, cache coherency, and some stuff on NUMA. And we'll be doing exercises on the Cray. Now, I've got a little bit of spiel at the start. Why are we using the Cray? Well, the Cray's got a 32-core Interlagos AMD processor in it, which illustrates almost all the issues you want to look at. In fact, the Interlagos processor is actually almost a bit slightly too complicated. It has too many features, but I've noted that in the practice session. But it has multiple levels of cache, some of which are private, some of which are shared, some of which are shared between more things. There's multiple levels of NUMA between different dies on a processor and between different sockets on the board. So it has all those levels on it. But the reason why I wanted to use the Cray is that because the Cray has because the Cray is designed purely for HPC, it doesn't have a general purpose Linux, it has a very stripped down Linux. And the AP run command, which you use to launch programs, gives you complete control of thread placement. You can say, I want thread 1 to be on core 15 and thread 2 to be on core 6, and they won't move. So you can actually play around with these issues, whereas if you're on a general laptop, who knows where stuff wanders around to. It's very hard to isolate particular cache issues because you don't quite know what's going on. This material was mostly developed by a colleague of mine, Mark Bull, and we run a one-year master's course at EPCC. It's just called the MSc in High Performance Computing, and all this material so I've taken from about 2 or 3 different courses and put it together. So I hope there may be you might see the seams in various places, hopefully not. But this all just comes from material we teach on our master's course. So if you've got any students or you teach any undergraduates who want to learn about HPC, then I'd encourage them to look at EPCC and our MSc. So I'm going to talk about why caches are needed, how they work, and the design and the performance. So, why are caches needed? Well, we don't want caches. We don't want parallel computing. Nobody wants parallel computing. We want an infinitely fast processor. Aren't going to have it, right? So we need multiple cores, multiple processors. We want infinitely fast memory. We're not going to get it. We need caches, and it's quite dramatic. It really is quite dramatic. So, in the 80s, there was this balance. CPU and memory cycles were about a microsecond. That's saying you're clocking at about a megahertz. And that's fine. And this is when people started to talk about flops. You characterize all your algorithms. People obsessively count, this takes 6.3 n squared flops, and they think that's important. Of course, it's meaningless now because this is only 20 years, another 10 years, but around about 2000, this had gone down by 3 orders of magnitude to 1 nanosecond, and this had gone down by 1 order of magnitude to 100 nanoseconds. So, memory load is 2 orders of magnitude more expensive than floating point add. So I know everyone says it, but this has been true for 20. I first noticed it on the Intel i860 way back in the early 90s, and it seems to take a long time to permeate, but flops don't matter, they're free. And I know everyone says that, and then you read any paper, they talk about how many floating point operations they do, what the complexity count of their algorithm is. It's all meaningless, right? This is absolutely meaningless, right? This is all that matters. This is all that matters. So, it's very simple. Programs exhibit some degree of locality. You reuse data, but you also reuse instructions, of course. Scientific codes especially spin around in loops a lot. And the 2 types of data locality are temporal locality and spatial locality. Temporal locality is obvious. A recently accessed item is likely to be reused in the near future. If X is read now, it's likely to be read again or written soon. And spatial locality is because we deal with arrays, hopefully. Hopefully we deal with arrays. We don't have linked lists or things like that. If we've read yi, we're likely to read yi plus 1 in the near future. And from this, it's a very, very common sense. There are a number of common sense things you can do. And I do like analogies. Let's think we're in the old days where we had books, and I want to read a line on page 53 of a book. So I go to the library. I don't take the book out, read line 53, put the book back, and go home, right? Because I probably want to read line 53 again. I probably want to read the next line, line 54, okay? So I photocopy the page, okay? Unfortunately, page and line means them. So I photocopy the page of the book, and I take it home. So I put it on my table, okay? But I might have room for 10 pages on my table, okay? So I want to be able to access them. So so the first thing is you want to read a small amount, but you take a big amount, right? And a fixed bit. You don't take 10 forward and 10 back. You take all of the printed page that the line of text is on. That's what you take, all of it, whether you need it or not. And then you've got to put it somewhere on your desk, and there's 10 places to put it, so you just use the last number. If it's page 83, you don't put it in position 3. Page 97, you put it in position 7, so you've got them all lined up here. You have to remember what they are, so you've put page 97 in position 7, but you have to put 9 above it to remember that's page 97. Because the next time you want to read, I want to read page 107, okay? I've got a 7, but it's the wrong one, it's 9, it's not 10, okay? So the concepts of caching are just completely common sense. That's what you would do when you photocopy a book in the library and bring it back. So, you exploit temporal locality because you might want to read the same bit of text twice in a row. You exploit spatial locality because you might want to read the next bit of text on the page. And you store them locally where they're quick. So what cache memory is just, like your desk. You have main memory, which is the library, have the processor, which is you, and you cache stuff. You keep copies locally on your desk. And you have some scheme for indexing them so that you can easily find them when you need them. So you also cache instructions. You very, very rarely have to worry about the instruction cache. In my experience, I only ever once ran out of instruction cache. Yeah, so I was writing assembly language, so I wrote a C program to generate the assembly. I couldn't be bothered putting the loops in the assembly code because it was too hard, because it was now LU factorization. So I just wrote it all out, and I ended up with 68 kilobytes of code, and the instruction cache on the i860 was only 64, or I can't remember. And then your performance just drops through the floor. So if you run out of instruction cache, you'll rarely do that. Okay, so fetching out of cache is much quicker than fetching from main memory. So here we're saying that fetching data from cache is the same as accessing a register, effectively, around about a cycle. But the cache is much smaller than main memory, simply because it costs more. It takes up more physical space on the chip, and real estate costs money. So the terminology is, as I said, even if you want to read a bit, you don't read a bit, you read a lot of data, and that's called a block or a line. So we talk about the cache block size, the cache line size. Typically, these are of order 32 to 128 bytes. I think on the Interlagos it's 64. I can't remember if it's 64 or 128. We'll find out anyway. So that means that even if you're using double precision complex numbers in Fortran, that's 16 bytes. You're going to be, even if you access one double precision complex number, you'll be loading more than one. Okay, so you will always load more data than you ask for, and if you don't use it, it's wasted. Okay, if you don't use that data, you've wasted that precious memory bandwidth. I mean, you can talk about how best to optimize this. So I'll probably talk about cached lines, but it's just a cached line is the minimum unit of data transfer from the memory. And so these are the design decisions you have to make. When should I photocopy my book? When should I take a copy of something? Where should I place it in the cache? How do I find stuff? How do I know if stuff is in the cache? If I take a cache miss, if I have to, I only have limited space in my cache. If I read some new data in and the space is already occupied, who do I replace? Who do I chuck out? What happens on writes? Now, you can clearly come up with perfect solutions to these, okay? Very easy to come up with a perfect solution, but they have to be fast. The processor has got like less than a nanosecond to decide. It can't really sit there and think, oh, well, maybe there, no. It's got to do it, within a cycle or two. It's very hard to come up with sophisticated strategies because they're too expensive. So the strategies are relatively simple. So typically, again, these are all typical. We always cache on reads. You can. There may be special instructions for non-caching reads and such like in certain systems, but typically you cache on read. If a memory location is read and there isn't a copy in the cache, and that's called a cache miss, you cache the data. You always cache on a cache miss. Writing is slightly more complicated. For instruction caches, there are no writes. So instruction caches are simpler. You're not allowed to write. Nowadays, you're not allowed to write self-modifying code on. I say unfortunately. It used to be fun to do, but you're not allowed to do it anymore. Instruction caches. We'll not talk about instruction caches because by and large, they're just there and they work. Okay. So where do we cache? Well, as I said, when you go into binary, you have lots of numbers and funny bits. But basically, all you're saying is, I've got 10 spaces on my desk. I've got page number 953. I'll just put it in location 3. That's the quickest thing to do. Just lop off all the stuff. And that's what you do. So, well, in the cache, if we had a 32-byte cache line, we might have a 32K cache. Each block has a number. So we have 1,024 slots, each of which can hold one piece of one cached line. So when we read some data from cache, remember the memory is gigabytes in size. We're going to have to put it somewhere, and we have less than a nanosecond to decide. So what we do is exactly like I did talking about the pages of a book. We just strip off bits. So we say, well, I always read 32 bits, so I don't worry about the first 5 bits. I don't care about that. And I take the next number of bits as the block index. So I just basically, there's a predetermined mapping. The whole of the memory maps to the cache. And then this is in a round-robin sense. So your first memory location maps to that address, then it maps around here, and then it goes back around again. So it's just a cyclic mapping, round-robin mapping cyclic mapping of your data to your cache. So I can say at boot up time, I know where every location is going to go in cache, which is useful if you want to do optimization. So technically, this block index, this is the data, we don't really care about this for caching. The block index is where it goes in the cache, but we have to remember where it came from, okay? Because I have to be able to distinguish between, in location 9, I need to know if it's page 79 or 159. So I have to remember the full address. So this entry is tagged with where it really came from, yeah? So you can decide whether to replace stuff. Sorry, I'm going the wrong way. So, okay. So if you just remove some bits and play around. Now this is a direct mapped cache, and this is clearly bad, because if I read page 79, I go all the way to the library, and I come back, and I put page 79 down, and I read page 99, I come all the way back, I throw away page 79, then I want page 79, I just end up, going back to and from the library too fast. So the next thing you can do is have set associativity. Say, look, I'm not going to have one slot for page 9. I'm going to have 2. Okay, so every cache line can go in more than one place. So you have the same setup, but you have more than one. And so a cache line might be mapped here, but you have more than one of these more than one table to put it on effectively. And again, you have to decide very quickly where to put it. So again, the calculation is exactly the same thing as before. We work out where in the set it should go by lopping off low and high bits. But then I've decided it's going to go into position 9, but I have more than one table. Does it go in position 9 on table 1, position 9 on table 2, position 9 on table 3? Where do I put it? Well, there's various choices. So if there are k blocks in a set, the cache is said to be k-way associative. So the way it's drawn here, it's saying that for block 0, there's more than one place. So this is two-way associative. It's like having, as I said, 2 tables for putting your photocopied pages on. If there's just one set, the cache is fully associative. These don't happen for data cache. I think the TLB is fully associative. Is that? I don't know more about virtual memory than I do. The virtual memory translation look-aside buffer, I think, is fully associative. But other than that, your normal data cache is going to be 2- or 4-way or 8-way associative. That's how it's going to work. So again, what you've done is you've loaded some data from memory. You realize it's got to go into position 1 in the cache, but you've got 2 choices. Where do you put it? Okay, and again, you've got less than a nanosecond to make that decision, probably. So we have to, okay, we'll come back to that later. So when we load an address, we have to check whether it's already cached. So we can say, well, okay, I know it's in position 9, but have I got that data? I've actually got that data. Well, as I said, each line in the cache remembers where the valid data came from, so you can check. And there's also a valid bit which says whether it's, you don't have to, there's a valid bit saying whether it contains any data or not. So what you do is, when you want to do a load, okay, so I want to load a memory address from memory and it resolves to position 1 in my cache. What I have to do is, this is two-way associative, I have to check that block and that block to see if it's been already loaded, okay? If it has been already loaded, I can just read it straight from the cache. If it hasn't, I then have to load it into the cache, and then I have a decision as to which one of these guys to kick out, okay? And that's a decision you have to make. And the reason that you can't make caches massively associative, 32-way associative, is that whenever you load some data, you have more and more places to check to see if you already, when you load some data from memory, the more associativity you have, the more places you have to check in the cache to see if you've already loaded it, and you don't have much time to do that. So you have to check the tags of all the valid blocks in the set for the target address. That's what you have to do, assuming they're valid. I mean, you can skip the ones which are invalid. And this is, I'll finish here before lunch. Which block do you replace, okay? You want to load data from memory. You find out where in your cache it goes. You look at all the sets which are there. You find out it's not already been loaded, so you load it, then you have to kick something out from the cache. What do you do? Well, you can just do it randomly. Replace a block in the selected set at random. I mean, basically, you can basically replace a block. You could replace a block at random in some way, or you would like to replace the least recently used. You'd like to say, well, which is the one I haven't used for, 100, 1,000 cycles, and get rid of that one. This is clearly better, but harder to implement. So, basically, LRU would be great because your cache would automatically flush out data which wasn't heavily used. And we'll be doing exercises on the Cray. Now, I've got a little bit of spiel at the start. Why are we using the Cray? Well, the Cray's got a 32-core Interlagos AMD processor in it, which illustrates almost all the issues you want to look at. In fact, the Interlagos processor is actually slightly too complicated. It has too many features, but I've noted that in the practice session. But it has multiple levels of control of thread placement. You can say, I want thread 1 to be on core 15 and thread 2 to be on core 6, and they won't move. So you can actually play around with these issues, whereas if you're on a general laptop, who knows where stuff wanders around to. It's very hard to isolate particular cache issues because you don't quite know what's going on. This material was mostly developed by a colleague of mine, Mark Bull, and we run a one-year master's course at EPCC. It's just called the MS Hash, some of which are private, some of which are shared, some of which are shared between more things. There's multiple levels of NUMA between different dies on a processor and between different sockets on the board. So it has all those levels on it. But the reason why I wanted to use the Cray is that because the Cray has because the Cray is designed purely for HPC, it doesn't have a general purpose Linux, it has a very stripped down Linux. And the AP run command which you use to launch programs gives you complete C and high performance computing, and all this material so I've taken from about 2 or 3 different courses and put it together, so I hope there may be some, you might see the seams in various places, hopefully not. But this all just comes from material we teach on our master's course. So if you've got any students or you teach any undergraduates who want to learn about HPC, then I'd encourage them to look at EPCC and our MSc. So I'm going to talk about why caches are needed, how they work, and the design and the performance. So Tim and Neil asked me if I could give some introductory material on just general multi-core memory caching issues. So that's what I'm going to do for this afternoon. I hope that this may be familiar to some of you, but hopefully the exercise will be interesting, even if the background's familiar. What I'm going to be doing is just giving some basic lectures, generic lectures about caching, memory issues, cache coherency, and some stuff on